Why did the white bear dissolve in water? Because it was polar. All right, NG Chemistry, Unit 5. This is about properties of water. And in particular, we're talking about how water, its properties, and how it affects Earth. This is really tied into Earth here. So, one of the important properties of water is that it carries minerals through the environment. Because of the fluidity of water, it's going to travel, it's going to carry minerals throughout the system. It can move down things like rivers, and it can even seep through soil, through the ground. And when this happens in caves, when the water seeps through the ground and into caves, it can bring with it minerals. If it goes seeps through rocks like limestone, limestone has calcite in it, which is calcium carbonate. And when that calcite gets dissolved and travels through into the caves with the water, it can start making deposits in the caves, and you get these really cool, unique formations. And when these formations come from the ceiling, they are called stalactites. So stalactites are calcite coming from the groundwater, or from the water seeping through the ground to the ceilings of caves. So this is limestone deposits that cling to the ceilings, and they're called stalactites. When this comes down, some of the water might drop to the floor, and it drops to the floor, leaving this limestone or calcite, which is calcium carbonate, onto the floor, and it will start to build up. The formations that build up are called stalagmites. Eventually, stalactites and stalagmites might reach each other, like in these examples here, and when they reach each other, this is called a column. Columns are when stalactites and stalagmites reach each other. And these are some formations in caves that happen due to water's properties of dissolving minerals. So just a refresher, something that dissolves something else, the thing that's dissolving is the solvent, and what gets dissolved is the solute. And when you have a solvent with a solute mixed together, these are called solutions. Water is considered the universal solvent because although you could dissolve something with a different with anything, water is the vast majority of the solvent in solutions. What makes water such a good solvent is that it is a polar molecule. Polar molecules have partially positive and partially negative sides to it. As we've learned before, water is bent, so it's not a linear molecule. It's made up of two hydrogens and one oxygen. The hydrogens are less electronegative than the oxygen. In other words, water has more electrons on the oxygen side of the water than on the hydrogen side of the water, making one side a little more positive than the other, and that's what polar means. Water is very effective at dissolving other polar molecules because what happens is opposites attract. So if the positive side is attracted to a partially negative side of another molecule, they will surround them and dissolve them in the water. That's what makes water a good solvent. Here's an example of putting a ionic compound into water. This would be sodium chloride. And if you take a look here, the positive sodium ions, the negative side of water would associate to it, and the negative side of water is the oxygen side. So the oxygen will surround those positively charged cations, the sodium here, and if you notice here, it'll cover all the way around it, and it will carry those ions through the water. So now the ions are free to move in the water, but they're surrounded by a cloud of water. And when you put the salt, which is a crystal, in water, you see it, but then it disappears. Well, it's not gone, but what's happening is the pieces are surrounded and being carried around in the solution by the water. So the negative side of water will attract to a positive cation, as opposed to the positive side of water, which is the hydrogens, will attract to a negative anion, like chloride. So the chloride pieces will be surrounded by the hydrogens, and the sodium pieces would be surrounded by the oxygen side of the water, and that's what makes it dissolve so well. Follow along with me a little backstory before I get into this slide. If you take a glass of water and you put some dirt in it, and you keep mixing it, it'll be very cloudy. It'll be this dark, cloudy glass of water. I mean, it would look like a colloid. You can't see through it, but it's not a colloid. It would be it's what's larger particles are called suspensions, because when you stop stirring it, the dirt will end up settling at the bottom of the glass, and you'll have a clear glass of water with dirt on the bottom. Point being is, when water moves fast, it can pick up more materials in it. So water in in geographically speaking, water distributes dissolved materials all around Earth's surface. When water's movement decreases, sediments can be deposited. So, just like stirring that glass of water, a river is moving fast and it can have a lot of sediment in it. And when it gets to a large body of water, it doesn't continually move fast, just keep moving like a river inside of an ocean. It will disperse out and slow down. And just like the glass of water, when it slows down, the dirt, the sediment will settle down. So if it's moving fast, it's carrying the sediment, and then as it slows down, the sediment starts getting deposited, and you get these really cool, unique geographical structures called deltas. And this would be a river delta where the water is emptying out into the ocean. Again, why does that happen? Because the water's slowing down, allowing the material to deposit. And when water is in a river, when it's moving, it's taking along from the banks and wherever it's coming across, it's taking along materials and sediment along with it. And over time, it will start carrying more and more and more, and that little teeny stream can get larger and larger and larger, allowing more water to fall into it when water's passing. And in an extreme example here, here's a picture of the Grand Canyon. Water would be running and cutting through thousands and millions of years, cutting down, and we can see canyons and small valleys being formed. So canyons and narrow valleys are formed when water carries away sediment over a long period of time. And that's another geographical feature that's caused by water's movement. Water being a universal solvent, it has important applications in biological systems as well. Water transports nutrients and minerals in biological systems. Because it's polar, it can surround things that are charged and other polar molecules, and it literally dissolves into the water. And therefore, when the water moves, it's carrying with it those substances. The human body or biological systems are by mass mostly water, which is a great thing because it allows nutrients and things to be easily carried through the system. If it wasn't able to dissolve things, heavier things would settle at your feet and your brain wouldn't be getting anything important. That would not be a good situation. To recap so far, one of the important properties of water is that it is a universal solvent. Why? What makes it a good solvent? It's because it's polar. The next thing we're going to talk about is the fact that water does something different than a lot of other substances when it goes from a liquid to a solid. Most substances, as it loses energy, it becomes less and less. It occupies less and less space or becomes more and more dense. So a gas will occupy a lot of space because gases are mostly empty space between the molecules. Liquids are much denser than gases because they will occupy less space. And most things, when they become solid, become even less dense than a liquid. For instance, if you had molten iron, you could picture molten iron and you put a block of iron in it, it would sink as it melts into that molten iron. But this is not the same with water. Water molecules expand when they freeze. So just like other things, steam or gaseous water would occupy more space than liquid water. However, when water gets cold enough and it freezes, it makes these geometrical patterns which actually occupy more space than it does as water. Now, this is an important thing because when it occupies more space, it becomes less dense. If you would imagine a lake when it's freezing or below, if water was didn't expand when it froze, if you were at the bottom of a lake or inside the lake, what you would see when it was cold, it would look like it was snowing because as the water starts to turn into a solid, it would fall to the bottom, becoming heavier. And you would see snow inside the water, and eventually it would start filling up, filling up, filling up. And if it was cold long enough, the whole lake would freeze over, killing all complicated life in there, like, the fish and things like that. But what happens is because ice is less dense, the water freezes and it stays to the top. You know this, when you put ice cubes in your drink, it floats to the top. So when it freezes, you get this layer of ice on the top, and eventually it freezes, and the fish are insulated in the bottom, and they're allowed to survive over these cold winters. So that's an important property of ice. Something what we're going to be focusing on more is the fact that when it expands, it can actually be quite damaging. If you've ever taken a water bottle and you threw it in the freezer, or a soda or something like that, threw it in the freezer to cool it down real quick and you forgot about it, you come back and you see that the container is broken. And that's because it expands, and it's quite strong when it expands. Let's talk about properties of this on Earth and what can happen here. Water can seep into little cracks in things like rocks and cement. So the water seeps into these little cracks. And then at night, if it gets below freezing, or at any time, but if it gets below freezing, I'm just going to use day and night kind of as an example. Um, as it freezes, it expands, and this is a bit dramatic, but it expands, widening up that crack. And then daytime comes, and the water melts, seeping deeper into the crack that it made. And then the next night it freezes again, and it gets larger and larger and larger. And this is how these cracks appear in roads, which eventually lead to potholes. And this process is called frost wedging. When water melts and freezes often, it will weather stone and cement. So in areas where it gets warm and cold often, where it kind of borders back and forth on that, we see a lot more damage to things like cement and rocks, and that is because of frost wedging. Here's an extreme example of frost wedging in Bryce Canyon, Utah. What happened here is you just got the soil, and in Bryce Canyon, it gets very cold. You can actually see the snow here. It gets very cold and very warm, back and forth, back and forth. And so the water seeps in, wedges, seeps in, wedges, and so it starts wedging and breaking apart the rocks, and then water washes away that sediment. And so as it happens, starts wedge, start wedge, start wedge, we start to get these really cool formations. These spires start to form, and it's really, really cool looking, beautiful sight there in Bryce Canyon. Bryce Canyon is still eroding rather quickly. It's eroding about 2 to 4 feet every 100 years, which means that we're looking at the erosion of this canyon in the process. We're watching this happen right before our eyes, and when it's finally all said and done, all these beautiful spires will eventually be gone. So this is a really cool picture of something that's going through a process. As far as Earth's timeline is concerned, this would be a relatively short period of time that you'd be able to see something like this. In our lifespan, it'll be there for our lifespan. But as far as Earth's is, it's rather short. The third property of water that's important is specific heat. So we talked about that it can dissolve things, we talked about that it expands when it cools, and now specific heat is the third and final property that we need to talk about with water. Every substance has a unique specific heat capacity. Specific heat is the amount of energy needed to change the temperature of a substance. The higher specific heat means that it's harder to change the temperature. Adding energy increases the temperature. So when you add energy to something, if it changes its temperature quickly, then that would mean it's got a low specific heat. If you add energy and it takes a long time for it to heat up, that means it's got a high specific heat. That's what I'm saying here. Higher specific heat, it's harder to change the temperature. It also holds that heat. So if it takes a long time to heat up, it will release a lot of heat also when it cools down. So things with a high specific heat are hard to increase its temperature, but also they will, as they lose that energy to the surroundings. So if the surroundings are cooler than the system will add heat to the surroundings, and if it has a high specific heat, it will add a lot more energy to the surroundings before it cools down. And why are we talking about this? Because water has a very high specific heat. Here are some values of specific heat. We've got water as a liquid. Remember, these parentheses represent what state of matter that they're in. So this is water as a liquid. Here's cement, which is a solid. And then at the bottom here, I've got some gases. And I put a line here because I want to talk about the top two first. So we're talking about the surface of Earth. Water's got a much higher specific heat than cement. And cement is made of rocks and things like that. So we could talk about like deserts and mountains and stuff like that would probably have a specific heat very similar to cement. What this means is, let's take a look at these units here. What this means is for water, it takes 4,182 joules. A joule is a measure of energy to change a kilogram of water by a degree Celsius, as opposed to cement takes 920 joules of energy to change a kilogram of cement by 1 degree Celsius. Joules come from the sun. Well, they can come from other things, but I'm going to talk about what the sun. The sun's heating up Earth. And let's pretend we've got a kilogram of cement and a kilogram of water near each other. If the sun hits Earth with roughly 4,000 joules, it's not focusing on the cement versus the water. It's hitting distributing all over the place evenly. What this means is water, when it gets 4,000 joules of energy, a kilogram of water will change by a degree Celsius, so it will start to warm up the water. However, if 4,000 joules hit the cement, it would actually change the cement, a kilogram of cement, by 4 degrees Celsius. So what this means is, because it's got a smaller specific heat, the cement will heat up faster. And I think you guys can relate to that if you've been to a pool on a hot day. Without any sandals on, you're standing on the cement and your feet are burning. Ow, 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 my feet are burning, my feet are burning. And you run across and you put your feet in the water, and the water is much cooler. Well, the sun's heating up both the cement and the water equally. It's setting its energy down to Earth, and it's getting both the same amount of joules. The difference is, because the cement has a low specific heat, its temperature is changing quicker than that of the water. And we can also relate this to giving off energy. At night, the sun's gone. There's no energy being given to the cement. There's no energy being given to the water. So the temperature starts to drop. And as the air cools, the heat from the ground is warmer than the atmosphere. So the cement will start to warm up the cold air, and the water will start to warm up the cold air. But for 4,000 of joules that are given to the air to warm it up, 4,000 joules that are given to the air to warm it up, the water would change, a kilogram of water would change by 1 degree Celsius. However, if 4,000 joules was given up by the cement, it would change by 4 degrees Celsius. So what happens is, at night, the cement cools down much faster than the water, and during the day, the cement warms up much faster than the water. This is also true with gases in our atmosphere. Our atmosphere is primarily nitrogen. It's 78% nitrogen. And so that nitrogen is the main gas in our atmosphere that's trapping heat for us, because just by mass it is. But we know that if you live in an area that's humid, it's got a higher specific heat than that of nitrogen, and it traps that heat better. So if you've been to places like Florida or like Houston, Georgia, anywhere on the East Coast, it can get quite humid, and it can be very, very uncomfortable at night because that heat gets trapped and it holds it better. It doesn't cool down as fast. And this is what makes Earth stay warm even when the sun goes down. If we didn't have these gases in our atmosphere, when the sun goes down, the opposite side of Earth would get extremely cold. So it kind of holds the temperature steady. So let's go back and talk about these surface substances. So I'm not talking about the atmosphere right now. I'm talking about the surface substances. Because water has a high specific heat, coastal areas tend to be more moderate. Because water's got a high specific heat, the energy of the sun will warm up the water slowly, and at night it will stay warm. So if you live near the coast, you've got this big kind of like battery saving energy, and so things don't get really cold at night because the water's warm, and during the day it doesn't get extremely hot because water is absorbing that heat as well. It's not magnifying. As opposed to if you go inland and you go away from a large body of water. So we got no oceans, we got no lakes, we go inland, and now we're talking about a specific heat more like, because again, if you're by an island or by the coast, you have this big battery of absorbing all this heat, the water. But if you go inland, you don't have that water, and you're going to be having a much lower specific heat. So when you're inland here, it can get very hot. And if we think of deserts, we think, yes, deserts are really, really hot. And yeah, I looked it up. Deserts' average temperature during the day is 100 degrees Fahrenheit or 32 Celsius. But a lot of people don't realize at night, deserts get extremely cold. The average temperature of a desert at night is 25 degrees Celsius or negative 3.9, I'm sorry, 25 degrees Fahrenheit or negative 3.9 Celsius. So it gets very, very extreme. Why is it so extreme when you go inland? Again, because there's no water here. There's nothing holding that heat, that that specific heat that kind of makes it so we don't have these huge fluctuations. Let's go one step further. On the moon would basically be rock. The moon has no water and it has no atmosphere. Do you think the temperature on the moon would be more moderate or more extreme when compared to Earth? Well, if there's no atmosphere trapping heat and there's uh, no water trapping heat, remember the moon is about the same distance from the sun as Earth is because it's orbiting Earth. It's not closer like Mercury and it's not further like Neptune. It's about the same distance, so it's getting about the same energy as Earth. So its temperature is about the same as Earth on average, but it would be much, much more extreme on the moon because it doesn't have things with specific heat, with a high specific heat trapping that energy. It has no atmosphere, it has no water, and so yes, it gets very extreme on the moon. The moon gets up to 224 degrees Fahrenheit during the day. Oh, that's like a cold oven. I mean, we cook things a little bit hotter, but that's ridiculously not for life to be living on there. And at night, it drops to negative 298 degrees Fahrenheit. Wow, that's almost negative 300 degrees Fahrenheit. So it's shifting back and forth between day and night, almost 500 degrees Fahrenheit, which extremely extreme changes here. And again, why is it such an extreme shift on the moon if it's getting the same amount of energy? Because the moon doesn't have things with high specific heat trapping it. It heats up quick and it cools down quick. Water not only transfers materials around Earth, but it also transfers energy around Earth. If we take a look here, you can see energy being added to a lake or the ocean, and that energy makes molecules of water evaporate. That evaporated water has more energy than the liquid. The gaseous water has more energy than the liquid water. It can then go up and cool down, condensating into clouds, and then eventually falling back down to Earth as precipitation. That water can then flow back into a cycle through rivers back into the lake or ocean, but it could also seep into the ground, and the groundwater could go back to the lakes and oceans also. Seeping into the ground is called percolation, and plants can then also pull water from the ground in something called transpiration. And this is what happens when you have photosynthesis at the leaves. It's using the water up, and you have the water going up through the xylem and phloem in the trees or the plants themselves through the roots all the way up. And as it pulls out, it's kind of like just sucking on a straw, where it just pulls the water out of the ground as well, and then the water goes back into the atmosphere. Important point to note, as the water cycle, there is no dead end to this. We're not going to run out of water, and we're not going to gain water. It goes through a cycle. Although it can be trapped in different stages for long periods of time, you're still going to have that water. For instance, when the oceans drop, that's usually because water is now being formed as solid, and it's becoming glaciers. And if it heats up and melts those glaciers, the oceans can then rise. But you're not going to have more water than we have. The final thing we're going to talk about, and again, this has to do with the specific heat of water, water trapping heat and energy, is an effect of snow. And you get a lot of heavy snow near lakes. This is called lake effect snow. And what happens is the reason for this, I should say, is water has a high specific heat. So when things cool down, the water will keep that heat faster than the air around it and the ground. And so as cold wind blows across and it gets towards the water, it starts to go across the warm water. The air warms and collects moisture at the lake. So this cold air blows, it gets to a lake, and it starts warming up. And as it warms up, the particles in the air start moving faster. The faster they move, the further apart they get. And the further apart they get per volume means it's less dense. So this less dense warm air starts to rise, and cold air replaces it. And that's actually what causes wind, is the difference in temperature on the land or in the atmosphere. because of the land. So the air comes, it rises, and it starts to then condensate into clouds. And if there's a mountain here, it will rise even faster as it ramps up that mountain, which will condensate even quicker and get a lot more dramatic snowfall. So the moisture builds up and the clouds causing lots and lots of snowfall. So you get an unusual amount of snowfall in areas that are close to lakes and rivers because of this lake effect snow. Okay, guys, I just want to end this video with just a call out for something maybe you can do to help change the world. And that is help us with a ban of dihydrogen monoxide. Dihydrogen monoxide is considered the invisible killer. For your information, DHMO is colorless, odorless, tasteless, and kills thousands of people every year. Most of these deaths are caused by accidental inhalation of DHMO in its liquid form, but the dangers of dihydrogen monoxide do not end there. Prolonged exposure to its solid form causes tissue damage, and contact in its gaseous form causes burns. Dihydrogen monoxide is used widespread. For those who have become dependent on it, DHMO withdrawal means death. DHMO can be an environmental hazard. It's a major component of acid rain. It contributes to the greenhouse effect and leads to the erosion of natural landscapes and hastens the corrosion of most metals. Being so prevalent, DHMO contamination is at epidemic proportions. Despite the dangers, DHMO is often used as an industrial solvent, as a fire retardant in nuclear power plants, and in certain food products. Companies dump waste DHMO into rivers and the ocean, and nothing can be done to stop it because the practice is still legal. The American government and the United Nations have refused to ban the product. Distribution or use of this chemical, due to its economic importance, continues. The Navy and certain other military organizations are highly dependent on DHMO for various purposes. Military facilities receive tons of it through sophisticated underground distribution network. It is also stored in large quantities for military emergencies. But it's not too late, people. Please act now. Contact your congressman, educate the public, and let's work together to do something good for our planet.